So I am considering that you already know BJTs, okay, bipolar junction transistors, and I will give a quick overview and then I will start with a few questions that I think can be important from gates point of view. I haven't taken any gate previous year question, but I have taken questions from a standard book, and I think similar questions can be framed in gate. If you are able to solve these questions, then you will be able to solve the previous year ones also. Okay. So let's have a quick overview first. So you know, for BJT, bipolar junction transistor, I am not going into the physics of it. The symbol is this for NPN, and this is for PNP. The carriers differ because there is the majority carrier effect here. So the electrons and holes, because of that, the current direction is different. So for NPN, this is your base. So current IB, IC, IE. Okay, so you remember this arrow. Okay, so this arrow is in this direction, so the current IE is in this direction. Okay, and this is direction here inside. This is IE, the main current is flowing here. This is IC, this is IB. Okay, so no need to memorize it any like this. You can simply see the symbol and you can understand what is the direction of the current. Okay, now since this is the direction of the current, how we annotate the voltages? So this is plus, this is minus. Okay, so plus minus VBE, this is plus, this is minus VCE. That means VB is greater than VE and VC is greater than VE. Okay, so VB positive, VC positive. Okay, now this is the condition. So first of all, the first condition is for actually keeping the base on. So base is on in this way. So first you have to put this base on. Okay, now for PNP, what will happen? PNP, this is plus, this is minus. So this is VEB positive. Okay, so here VE is greater than VB. So VEB is positive. So for this to get it on. Okay, and then VE is greater than VC. Okay, now why is it so? So in a transistor, if you see, this is nothing but this is N, P, N, and if you see Ebers-Moll model, you will see this is can be connected like this, like it can be shown in this way. But two diodes connected like this back to back will not give you transistorized action. It only gives transistorized action in some cases. Okay, if you want to read about it, that is explained in Streetman Banerjee's book. But apart from that, you have to remember, like, this is how it comes out to be, Ebers-Moll model. So NPN, and if you see, what did I say? So I made some mistake. So this is P, this is N, right? So this will be in this way, NPN. So NPN, and therefore the diode's negative terminal you see is connected here, right? The negative terminal of diode is connected in this terminals, and this is the positive ones. Okay, so now if you want to make the for base to emitter junction, so this is called base and emitter and collector. So base and emitter. So if you want to make base to emitter forward bias, that is on, we have to give VBE as positive, right? It should be some positive voltage. And since it is same as the drop of the diode, we say it is approximately VBE is equals to either 0.6 or 0.7 you have to reach, or sometimes in some cases 0.8 is also given. Okay. So once VBE is forward biased, then we come to VCE. So this junction, right, VCE, and the diode is connected where? Between C and B. So we will check. So for the output for the collector junction to be forward bias or reverse bias, we will check that. So now if you put VCB, okay, if you put VCB as positive, that means there is a plus sign here and there is a minus sign here. So plus will make the diode reverse bias. So VCB makes the C to B junction reverse bias. Remember, this is in case of NPN. I have written the transistor, right? So this is NPN. So this region of operation where VBE is positive and VCB is negative, here you see, VCB is also positive, so that CB is reverse bias and BE is forward bias. In this condition, you will see that any small change in the current IB, okay, any small change in current IB results in a bigger change in IC, bigger change in IC, okay, and that change factor is given by beta, which is the gain, current gain. Only in this condition, and therefore this is called as the active region. Okay, so now you would have heard about region of operation and stuff like that. So how to find out region of operation of the BJT? So BJT is region of operation. So if you are given a circuit, to find out the region of operation, 1 mark question is possible, simple for finding out region of operation. You will be given a circuit, normal circuit, which will be biased with a DC source, and there will be some collector resistance and a voltage source connected here, power supply, and now they will ask you to find the region of operation. So depending upon these values, these design parameter values, you have to find out VBE, VCB, and you have to see whether these are coming as, so this has to be positive and greater than 0.6 volts, right? And this has to be simple, this has to be positive for this to be reverse bias, and therefore this is in active region. Now how to find VCB? For that, you see VCB can be written as VCE minus VEB. How am I writing this? So VCB can be written as VC minus VE minus of this has to be BE minus of VB minus VE, right? So therefore, what you will do, you will find out VCE, which is the voltage here, VCE, and VBE also you will know. And if you subtract both of this, they have to come positive. Okay, so VCE has to be normally a voltage which should be greater than 0.8 volts for it to be in active region. You understood? It has to be greater than VCE, has to be greater than VBE, and only in this case VCB will be positive and your output will be reverse biased. Output collector is reverse biased, right? And input is VBE, which has to be greater than 0.8 anyways, 0.6 or whatever is a VBE cutoff. VBE cutoff. Is this clear? So this was quick thing of region of operation. So I have written, so okay, so now for PNP, so many people get confused as to what to be done to PNP. So nothing, but in PNP everything goes opposite. So what will happen? See, in PNP the transistor will be like this, right? Right? So whatever the voltages are given, you will have to just simply invert it. So VEC, this is plus minus VEB. Okay, and the the source will also be connected in this way. It will be in this kind of a connection. Okay, so plus minus VEB will be positive, so that VEB is positive, and this will be obviously greater. So VCC will be something higher in value. Okay, so am I doing some mistake here? Let me check. Yes, I think so. This has to be positive. Sorry. Yes. So now when VCC is sufficiently higher than VB, so what will happen? This will be EB will be nothing but right. So this is the thing, and this has to be 0.8. Okay, you can check it. Okay, and in these cases you only have to apply KVL equations and find out the voltages, and corresponding conditions will give you region of operation of the BJT. So now this I have written. So in active region VCB is positive for NPN, and VB should be greater than VB threshold or cutoff. Okay, and for PNP it is just the opposite. VCB should be negative, or we can say VBC is positive. Okay, so this is nothing but VBC is positive, and of course VEB has to be greater than VEB threshold. This remains the same, only I have changed BE to EB. Okay, suppose if you are saying B, then negative of VBE is supposed to be greater than negative of VBE threshold, because the BE for a PNP will be negative, so automatically it will be positive. Okay, so this is active region, and in this case IC is given by beta times IB. Only in active region it is given by IC is given by beta times IB. Now in saturation region, what will happen? If you get VCB negative, suppose you are getting VCB negative, then you know that your output is forward bias. Collector is forward bias. Now if VB is also greater than VBT, now you know that the base junction is also forward bias. So if both junctions are forward bias, so both B2E and C2E, C2B are forward biased, then it is in saturation. Okay, that means that even if you increase the base current by a small amount, there is no change in IC. So IB and IC actually do not relate to each other in saturation region. Okay, so what will be the condition? If you separately find IB and IC, you will see they follow this condition for saturation. So what do I mean by this? Suppose your circuit is the parameters are given in such a way that when you found the values, what happened was that you got this condition. Suppose VCB you got as negative. So what do I mean by this? That you did not sufficiently apply a voltage here, so that VC came out to be, let's say VC came out to be 0.6 volts. You applied KCL, KVL, everything. Okay. So how will you solve this question? So if there is RB, RC, VCC, VB, let's say. Okay. So what we will do? You will find VBE first. What will be VBE? VBE will be VB minus IB times RB. Right? IB times RB. Now what you will do? You will find VCE. What will be VCE? VCE will be VCC minus IC times RC. Right? Now VCC minus, what you can do? You will assume it is in active region. We will assume it is in active region. Okay, and then we will simply write beta times IB into RC is VCE. Okay, now from here the values will be given. You will find some values Okay, so let's say you got 0.6 volts here, and let's say when you found VCE, you got something as 0.5 volts. Okay, now what you do, you will find VCB. Now if you find VCB, it comes out to be negative, minus 0.1 volt. Okay, that means it's a forward bias junction. Okay, so this is a forward bias junction, right? But VBE is greater than VBE cutoff. Okay, I'm saying VB is greater than VB cutoff. So now what we will do in this case, again you will have to apply these two equations, but you cannot substitute IC with beta times IB. IC will not be equal to beta times IB. So in this case what we do, we assume VCE to be its saturation value, which is nothing but 0.2 volts, or it will be given in the question. So you will assume VCE sat as 0.2 volts. You will again write the same equations. You will again write the same equations. But now IB and IC both are unknowns. You cannot substitute IC because IC is not equal to beta times IB anymore, since it is in saturation. So what you will do, you will substitute this value, you will substitute VB as 0.6 volt, which you have earlier got, that is correct. So that will be 0.6 equals to something VB minus IB times into RB, some value will be given. Okay, and here will be 0.2 VCC, some value will be given, IC into RC, again some value will be given. So these values are given. So therefore what are the unknowns? IB and IC, right? So from here you will be, your system will come out to be kind of a linear equation with two variables. Sorry, linear equation with one variable, it will come out to be something like this. Okay, and then you can solve it and get the answer. Okay, you will have to separately solve it and you will get the answer from there. Okay, so this is a linear equation with one variable, right? So from here, if all the values are given, you will find IB from here and IC separately from here. So your IB will be something, let's say you will get some value of IB, and your IC will also be something, so X and Y, and you will see that this value of IB will always be greater than IC by beta. So if this is satisfied, it is in saturation. So we proceed in this way with this kind of question. You assume it is in active region, you solve it, and then you see that whether your assumption was correct or not. If your assumption is correct, it is in active region, your answers are correct. If your assumption came out to be wrong, because you will find VCB, right? So your assumptions will come out to be wrong, then you have to check whether it is in saturation. So you will see that this current will arrive. Okay, the other region which is there is cutoff. So identifying cutoff is very easy. Normally if VBE will be less than VBE cutoff, then the input junction is reverse bias. So VB2 is reverse bias and therefore it can be in cutoff. Okay, in this case normally you also find VCB. So if VCB is also in reverse bias, right, then this is said to be in cutoff. If VCB is forward bias, then it is in reverse active. Reverse active. Okay. So if VBE comes to be reverse bias, then you again find VCB. If VCB is reverse bias, it is in cutoff. If VCB is forward bias, it is in reverse active. Okay. Now, with this knowledge, let's go to one of the question. I'm not going to solve any question of region of operation because they are in abundance in internet. You can sort it out and solve it. If you want, I can solve it in next class, region of operation. Okay. So now you see there is one formula which relates the BJT collector current to saturation current of a normal BJT. Okay. So IS is a saturation current. BE is base to emitter voltage. VT is the thermal voltage. Okay, which is given as 26 millivolts at your 300 degree Kelvin something. Okay, so that is your normal thing. So VT is thermal voltage is 26 millivolts. Now Is is given as by this. So this you would have read in the semiconductor chapter, which is nothing but area of emitter. Okay, area of the emitter junction, the charge, dn, diffusion constant of the electron, ni square, ni is the intrinsic density, nb, wb. Nb is the doping concentration of base, wb is the width of the base. Okay, so normally you will see that if they want to make it a kind of a trick question, you will see that they normally will utilize the relation of saturation current with either AE or NB or WB. They use this. Okay, mainly they will use IS relationship with emitter area or base doping and width. Okay, so now we come to one first question. So you also please note down this, that IS is directly proportional to emitter's area and it is inversely proportional to the doping concentration of base as well as the width of the base. Okay, so now question is that we have Q1 and Q2 are identical and they operate in active mode, right? And we have to determine V1 minus V2 such that IC1 equals to 10 times IC2. So I give you 1 minute. Please note down this question and try to analyze and think what is to be done. Then we will proceed. Okay. Okay. So now you see what is V1. So V1 is nothing but VBE1, right? If this is transistor Q1, this is Q2, this is let's say QX, Q3. Okay. So now VBE1 is nothing but V1 and VBE2 is nothing but V2, right? This is nothing but a KVL here, right? So this I hope is clear. Now what we have seen this relation. IC is equals to IS e to the power VBE by VT. So therefore IC1 will be IS1 e to the power VBE1 by VT and IC2 will be IS2 e to the power VBE2 by VT. Now in this kind of question, silly mistakes can happen if you don't identify your transistors properly. So it is given IC1 equals to 10 times IC2. So be careful about Q1 and Q2, about the transistor notation that is given in the question. Don't take opposite things. If you take opposite, your answer will exactly come 1 upon whatever you want, right? So in that case, if it's a numerical answer type, you will mess it up. Okay. So what will be V1 minus V2 such that IC1 is equals to 10 times IC2. Okay. So there is one more relationship of IC1 and IC2. What is that? IX equals to IC1 plus IC2. Right? This won't be used in the question, but you can see that. Okay? IX equals to IC1 plus IC2. Now what will happen? IC1 is given as 10 times IC2. So I can simply take the ratio. And also the transistors are identical. So Q1 and Q2 are completely identical transistors. That means IS1 equals to IS2. But VBE is the value which is dependent on what? biasing we are giving from outside, that is V1 and V2. So V1 and V2 are nothing but the biasing voltages. So that will decide your VB. Okay. So now if I take the ratio IC1 by IC2 equals to e to the power VB1 by VT upon e to the power VB2 upon VT. So this is nothing but IC1 by IC2 from the property of exponents, e to the power VB1 minus VB2 divided by VT, right? I hope you know this much maths. Okay. So now IC1 is nothing but what was given? IC1 is 10 times IC2. So 10 times IC2 upon IC2 e to the power VB1 minus VB2 upon VT. If nothing is given, VT is to be taken as 26 millivolts, or they will provide it in question. So now please solve this and tell me what you are getting. So you have to solve 10 equals to e to the power VB1 minus VB2 upon 0.026 in volts, right? Or 26 millivolts. Okay. So this is nothing but natural log of 10. Okay. Please remember, this is not log base 10. This is natural log of 10 equals to VB1 minus VB2 0.026. So when you solve this, what you will get? Natural log of 10 into 0.026 is nothing but 0.0598 volts. And you had to find this only. They had asked V1 minus V2. So this is nothing but equal to V1 minus V2. Okay. So this is how this question was solved. So I'll keep it here for some time so that you guys can note it down. Please let me know once you are done, okay?
Done, ma'am.
Okay then. So from here you see this relation. You can note down this relation which is valid for the active region of operation, right? So IC we saw that it is equals to IS e to the power VB by VT, and likewise IB will be IC by beta and IE will be IC plus IB, right? Okay. So now let's come to another question. So normally area of discrete transistors is 500 micron cross 500 micron. Area of integrated devices are 0.5 micron cross 0.2 micron. So what does it mean? So first you should understand. So let me give a brief overview of this thing. So what is a discrete transistor? The BJTs that you have normally used. Okay. Normally you would have used this thing in your lab with breadboards. Right? So this is a discrete transistor. Okay. And when you say a transistor in IC, integrated circuits transistor, they are very small devices. Okay. And they are normally used with other things. So there, I don't know whether you have seen it or not. In CMOS, you normally see this kind of a configuration, right? So what you see in CMOS, they will show you the cross-sectional view and all those things. So the ICs which are there in these things will have in integrated devices, they will be very small. Okay, and these are bigger transistors. Okay, so that is the difference. That is the meaning of discrete transistors and integrated circuits. Okay, so now area of discrete transistors is more obviously, you can see it is 500 microns. 1,000 times of what is integrated devices, which is 0.5 micron. Okay, and even 0.5 micron is also very big. For if you go to nanometer technologies, they have now started using FinFETs, which are 7 nanometers. Okay, so anyways, integrated devices are 0.5 micron into 0.2 micron, and area of discrete transistors is 500 micron into 500 micron. So assuming other device parameters are identical, so all other device parameters are identical. Now determine the difference between base emitter voltage of two such transistors for equal collector current. Now I had shown you that formula, okay, that I had asked you to write it down. And I told you that they normally will ask either with a emitter area or with the doping levels. Okay, so now they have not specifically mentioned emitter area, but that is the area you have to take. Okay, so now area of discrete transistors is given, integrated is given. So you know now the relationship, right? You know that IS is directly proportional to AE. Okay, you know this. So now what will be the thing? So IC is nothing but, let me say ICD. ICD stands for collector current of discrete transistors. So ICD is nothing but ISD e to the power VBE discrete, that is D again, VBE D upon VT. Yeah, and ICI, which is integrated. Okay, ICI is integrated. There is ISI e to the power VBEI upon VT. Okay, okay, this was just fine. So now let us take the ratio. So ICD by ICI is nothing but ISD upon ISI, and I am given nothing else but the ratio of the area, and I am asked what will be the sorry, what, yeah, so what I'm asked, okay, I'm asked what is the difference between base emitter voltages. So VBED minus VBEI, that is what I'm asked. Okay, and the condition which is given is they should have equal collector currents. If this condition is not given, this question is not solvable, right? So equal collector current, so that means this ratio is going to be 1, right? And here what will be there? E to the power VBD minus VBI upon VT. I have taken the ratio, right? And just in previous question we saw that exponential, it will be negative. Okay, so therefore now I can write, so what will we write ISD and ISI as? So ISD by ISI is nothing but AED upon AEI, area of discrete transistor and area of integrated circuits. So ISD, because we have seen that ISD is directly proportional to AED, and we have seen that ISI is directly proportional to AEI. So if you take the ratio, it will come with a equal sign. Okay, now this ratio is nothing but what? 500 micron into 500 micron upon 0.5 micron into 0.2 micron, right? So everything cancels out. What will be the answer? So 0.5 into 0.2 is 0.1, and 500 into 500 is 25. So the answer is 25 into 10 to the power 5. Please check. So 25 into 10 to the power 5. So now 1 equals to 25 into 10 to the power 5 e to the power VBD minus VB1 by VT. So please solve and tell me what answer you are getting. You know how to solve it, right? You take the 25 with this side, 1 upon 25 into 10 to the power 5 will be equals to e to the power delta VB, I am writing for short, by VT. Okay, and then you take the natural log and multiply with VT. So delta VB will be VT into natural log 1 upon 25 into 10 to the power 5. So please tell me what you are getting. Are you getting 0.323? Just check once more. So VT you have to take at 0.026, right? 26 millivolts. You are close but not exact. And I think here mistake should not happen. If it is a numerical answer type, you cannot write it's 0.383. So you cannot write 0.383 as 0.323, okay? 0.323 will be wrong, because if it is a numerical answer type, I don't think they will keep it in a range. They might, but I don't know. They might keep it in a range of 0.3 to 0.4, since there is a natural log applicable. So they might keep it in a range, but better be specific. Okay. Okay. So this you guys have solved. Good. So I hope this question you have understood. Okay. So, and I think previous year questions, these things have been asked, right? And I have not taken it from any previous year question, but these kind of questions have been asked. So I have taken it from, I'll tell you the books. So go through Razavi's Fundamentals of Microelectronics, not the analog design book. Okay, go through this book. Don't see the analog design book. That is not for you. Okay, this book will be for you. Yeah, I think even MOSFETs also this book will cover. This is a good book. Razavi Fundamentals of Microelectronics. Okay, I've taken it from there. Okay, so now come to another question, which is quite solvable kind of a question. So consider the circuit shown in figure where ISQ is equals to given and whatever the value is given, and VBE is given as 800 millivolts or 0.8 volts. Assume beta is 100. First, determine the transistor terminal currents and voltages. What do you mean by terminal currents and voltages? So what is transistor's terminal? Emitter, base, and collector. So terminal current and voltages means VB, VC, VE, and IC, IB, IE. Okay. Determine the maximum value of RC that permits operation in active mode. So this is the interesting part. This is where gate questions can come from. Determine the maximum value of RC that permits operation in active mode. Okay. So what is happening in a BJT? When you are giving the bias voltages, it gets biased to some region of operation, and you see that either it is reverse bias, forward bias, whatever, and it all depends upon whatever your values of the design parameters are. So VCC, RC is something you are externally connecting, right? So that is what will decide the region of operation. So therefore the question is framed in this manner. Okay. So first part, I think determine the transistor terminal currents and voltages. So can you guys do that? It's easy, right? VBE, we are able to see what VBE is. It's given 0.8 volts. Tell me what is the value of these things. So Vx is given in a graph, right? Vx is given in a graphical format. But how will you know IC? You cannot find VCE if you don't know IC. Anyone? Okay. So just now you saw the formula, right? So you see IS is given in the question. So put the values. Tell me what IC is. What is the value of IC you guys are getting? You understood? In the question, IC is not given anywhere. IB is also not given. Right? So from where will you find IC? IS value was given. IS was given. Saturation current was given. VBE is given. And similarly, they can also, if they want to ask a 2 marks question, what they will do, a theoretical question, they will not give you IS, but they will give you the parameters from where you can find IS. They will give you emitter area, they will give you NI value, WB, NB, Q, DN. All these values they will give you, and they will ask you this kind of a question. You have to first find IS and then proceed. So please tell us what are the values of IC you guys are getting. Please be careful about the units. So IS was given as 5 into 10 to the power minus 17 and this is in amperes. Yes, so we are getting 1.153 milliampere. Good. So IC is 1.153 milliampere. Now they are asking beta is 100. Right? So now you know that this transistor, okay, this transistor at first VB is 0.8. So input I know. I have to now figure out what is VCB. So accordingly now my transistor will be either in active or in saturation or either in active or in saturation because input is already forward bias, right? Okay. So now Vx is given. This is Vx, this point, right? Vx. So what is Vx? Vx is nothing but VCE, right? Okay. So Vx is equals to 2 minus IC into 0.5 K. So it's my habit to write everything in terms of kilo ohms and milliampere, so that when it gets multiplied, everything is in volts. This is my habit, normal habit. Okay. So I write in that way only. So IC into 0.5 K. 2 minus IC into 0.5 K. IC you have figured out. Okay. 2 minus 1.153 into 0.5. So what is Vx? Vx will be, you should get the same value here. So now again, IS was given, VB was given. If we would have seen that, so the problem is that they have not asked for a single RC value. If they had asked for RC 0.5K, what is IC? Then you would have directly found it out from using this value 1.424. But in normal question, if this kind of graph is not given, then you have to use IS and find it out. Okay, or otherwise you can just put in the value and see. I think you should get 1.424. Yeah, we are getting 1.424. Right? So verified. The graph is verified. Okay. Now they have asked for the RC's value for which it has to be in active mode. So now you know for active mode VCB is positive, which is VCE minus VBE. So I should have any value which is greater than 0.8 volt. Right? So VCE should be greater than 0.8 volt for VBE. So what is the lowest point? What can be VCE? So here you can see the edge point will be 0.8, which is given here. You understood? So VCB is VCE minus VB. Now VCE has to be greater than 0.8. Okay. So what is the edge? Edge is 0.8, right? So where is that edge in the graph? For what value? RC 1041. That was the edge, right? Right? So therefore for RC equals to 1041 ohms. Okay, till that point my transistor will be in active region. As soon as you connect a RC of this value, the transistor will be out of active region. It will be in the edge basically. So here also you did not have to solve anything because it was given in the graph. Now suppose this graph was not there. Okay, this graph is not there. Then what you will do? So you will take 0.8 and you will substitute here. So 0.8 equals to 2 minus 1.153 into RC. From here you find RC, which will give you 1.041 kilo ohms, and that is your answer. If the graph is not there, you have to solve and get it. It is solvable. I hope you have understood the question. Please see whatever I have done. If there are any doubts, you ask me. Please see it for 2 minutes. Properly you see the question. Okay. So the graph was actually for help because this is an example problem of the book. So they have put all the things to put it in an explanatory manner. It may be there in the question. It may not be there in the question. Okay. If it comes in gate. Or you may be asked this graph itself. It is highly possible that you are given a question in which you are asked what is the graphical nature of VCE, and this is the graphical nature of VCE. So this is a good question. Okay. I hope you are understanding my point. In GATE, they can frame the question in any way. So this is a highly likely question that they ask you a graph of VCE and this is what you should get. Okay. So please note this question carefully and analyze it later. Shall we proceed?
Yes, ma'am.
Okay. Okay. So now coming to the transconductance quickly. Okay. So GM transconductance is given by D of IC by D of VB. So remember, now we are doing all as large signal analysis, right? So therefore everything is in capital. So DIC by DVB. So from where will you find out DIC by DVB? Again the same thing. So IC is IS into e to the power VB by VT. Okay. Now quickly tell me what you are getting. DIC by DVB as. So if VBE has to be differentiated, you will get 1 by VT in front, right? And IS was constant. And since it is e to the power x and differentiation of x, so this will be e to the power VB by VT, right? And this term here is nothing but IC, right? So you get IC by VT. So this is how you arrive at GM. So GM is nothing but given by IC by VT. Okay, and beta times GM, if you do 1 upon 1 upon beta times GM, this gives you R pi. So that is the relationship. Okay, and therefore beta is nothing but, did I do anything wrong again? Beta should be GM times R pi. I wrote it, sorry. This is beta upon GM. Sorry. So beta upon GM is nothing but R pi. Okay, and therefore beta is equals to GM times R pi. Okay, so this is also something that we normally use, and this is the formula. Okay, so now from here let us see another question. Consider the circuit shown. What happens to the transconductance of Q1 if the area of the device is increased by a factor of n? So now for a normal transistor, it is given that this its GM is this one. The collector current is IC naught. The base voltage is VB0. Now how will you increase the area of transistor? So what happens is in integrated circuits, how a transistor looks like is something like this. It will look like this, okay? So collector, base, emitters, let's say. Okay, and how do they increase the transistors thing? So you have these parameters in your software, and you can use increase them by either connecting them in parallel. So if you connect everything in parallel, what will happen? This area is increasing, right? This area is increasing because they are connected in parallel. Okay, so for increasing, what they do, they connect multiple transistors in parallel like this. Okay, so this is what is done in the question also. Okay, you see all the emitters are connected to ground, so they are all connected to ground. So this is a common connection. All collectors connected together, all base connected together. So therefore the transistor BJTs, n BJTs are connected in parallel, and this results in what? The collector current has to be now increased, right? So that all the transistors are biased. Okay, so that all the transistors are biased. So therefore what will happen if one transistor is having IC naught, then the total current is n times IC naught. And once the total current is n times IC naught, what is happening? So basically, if I redraw this, I think it will be easier to understand. So basically this is done. Okay. And this is one terminal, this is one terminal. So now this transistor in all together, this is nothing but a bigger transistor. Okay, which is having n times the area of each of these transistors. So each area is A0. So n times the area. And this current, this is IC0, like this. So this current is n times IC0. So now this VCC actually has to supply n times IC0. Okay, so this is n times IC0, and this is how your GM is increased. So for increasing the transconductance, you have to connect these devices in parallel. So the GM actually becomes n times GM naught. So this was the question. Okay, the question was, how will the transconductance increase? So since transconductance GM is nothing but IC upon VT, and IC is increased to n times the one IC of one BJT, therefore this is n times GM naught. Okay, please note this down. So this is the purpose of actually connecting transistors like this in parallel. The another place where it is used is current mirrors, right? Where you have to mirror the current. A similar thing is done, right? But there the collectors are not connected together. The collectors are different. So please note this down. This will be our last question. We will continue this in the next class only. So please try to go through the book if you have time, because this is peak time. So if you are giving GATE in February, I think, so you should keep on practicing question, and you will see these kind of questions are there in GATE previous year. Okay.